Dear conference participants, my name is Oksana Bahrii-Zaiats. The title of the research is Qualitative and Quantitative Comparative Analysis of Results of Numerical Simulation of Cyber-Physical Biosensor Systems. Nowadays, the concept of creation cyber-physical systems for various spheres of technology integration with human activity is actively developing. Cyber-physical systems are considered as intelligent systems, in which external devices, processors, physical objects, network equipment are integrated. The main purpose of cyber-physical system creation is to monitor the behavior of physical objects as components of such systems in real time. These are systems in which cybernetic means measuring, computing, control, communication interact with physical process in arbitrary objects. Cyber-physical systems are attracting more attention than ever thanks to the rapid development of the Internet of Things and its combination with artificial intelligence, machine learning, and the cloud. Cyber-physics of the system are identified with the manifestation of the fourth industrial revolution that is taking place in the modern world. Thus, there is also the physical possibility of using Internet of Things technology where signals from sensors and measuring instruments need to be used. Cyber-physical technologies are already transforming the way people interact with engineered systems in the real or physical world, just as the Internet has transformed the way people interact with information. Yet, due to their complexity, the developers of cyber-physical systems face a major problem: the lack of simulation tools and models for their design and analysis. In the slide, examples of the application of biosensors in the modern life are shown. Cyber-physical systems are systems that integrate computing elements with the physical components and processes. The computing elements coordinate the communicative action with sensors, which monitor cyber-physical indicators, and attractors, which modify the cyber and physical environment. Cyber-physical systems use sensors to connect all distributed intelligence in the environment to gain a deeper knowledge of the environment, which enables a more accurate action and tasks. Biosensors are analytical devices that use biochemical reactions to detect a wide range of chemical compounds, metabolites, medications, environmental pollutants, etc. Slide shows the principle of operation of cyber-physical biosensor system of medical and biological processes. First, a particle of the substance is measured, which is measured with a particle of the selective layer of the cyber-physical biosensor system, resulting in the formation of the product, which is converted by the converter into an electrical signal for data analysis. That is, the methods of molecular biology, electronics, and communications make it possible to monitor health, controlling chronic and preventing critical human conditions. A cyber-physical system typically consists of physical and cyber spaces with various sensors and actuators, as graphically shown in the slide. These spaces integrate computation and physical processes and are interconnected by the network layer for exchange of data between these two spaces. The development and implementation of sensors with different functions in practical use are one of the priority areas of modern electronics. Development of biosensors requires integration of knowledge in different subjects such as molecular biology, genetic and protein engineering, analytical chemistry, microelectronics, and nanotechnology. Nowadays, the integration between physical resources and computing leads to the creation of complicated computing systems with distributed parameters. Such systems are controlled or managed by integrated internet computing resources. In our work, the model of the cyber-physical biosensor system is based on the concept of the cyber-physical system, taking into account the peculiarities of intelligent immunosensor. With additional skills, dashed lines in the picture, the sensor expands to cyber-physical biosensor system. This provides more diagnostic information about the object of research. The cyber-physical biosensor system model based on the hexagonal lattice from used lattice differential equation is considered in the work. In this case, the cubic coordinate system is used for numbering of biopixel IJK. The model is based on such biological assumptions for an arbitrary biopixel. We consider a very simple construction of the late antigen antibody model for the hexagonal biopixel array, which is based on the known Martsenyuk model and uses the special operator S. V is the antigen concentration, F is the antibody concentration in the biopixel. The model is defined by the initial functions. Each colony is exposed to antigens produced in thick adjacent biopixels, which are separated by equal distances. Numerical experiments based on computer simulation were carried out taking into account an integer natural number n that characterizes the number of biopixels in the hexagonal lattice. This set of parameters ensured the fulfillment of sufficient conditions of local asymptotic stability. We observe qualitative changes in the behavior of biopixel of the model on the hexagonal lattice as a whole. And at the time tau 0.05 we have stable focus. For next values we observe the Hobbes bifurcation and chaotic behavior of the model. Also we got results for lattice images of antigens and antibodies. At tau 0.05 there is a stable focus. For tau 0.25 it is less pronounced running wave of antibodies, and for tau 0.287 it is more pronounced running wave of antibodies, which is present in the pictures. Also, lattice images of the probability of antigen binding to antibodies in the system was obtained in the work. For the computer simulation, we got next results. In the emerging Hobbes bifurcation and all fused paths correspond to the stable limit cycles for all points for tau bigger than 0.25. Also we got results for the model on the rectangular lattice, and analyzing the phase diagrams we can conclude that for tau 0.05 the solution of the system tends to a non-identical endemic state, which is the stable focus. For tau 0.22 we observe trajectories corresponding to stable nodes for all pixels, and for tau 0.23 there is a Hobbes bifurcation. Next value shows the stable elliptical limit cycles, and for values higher than the last we may observe the chaotic behavior of the system. Also for rectangular form we got the lattice images of antigens and antibodies, and for tau 0.05 we have the stable focus. For next value we have the less and more pronounced running wave of antibodies. And lastly, as a result of numerical analysis, the probabilities of antigen-antibody connections in the biopixels of the models under the study vary according to the laws of discrete dynamics. Analyzing the obtained results, it was concluded that when the value changes qualitatively, the behavior of the biopixel and the system changes. For tau 0.23 we have the Hobbes bifurcation, and the results of the numerical simulation obtained in the work allow to analyze the stability and compare the studied models taking into account the time delay. In the following research, it's necessary to offer mathematical models of intelligent systems of big data on the basis of other geometrical structures and to carry out research of their stability. Thank you very much for your attention.